This is Homeschool 101, a collaboration between ABS Television and the Ministry of Education. Stay attentive and attempt all activities. And now, today's lesson.
Hello everyone and welcome to Homeschooling 101. For today's integrated mathematics class, we will be looking at exponents and logarithms. At the end of today's class, you should be able to state real-life applications of exponents and logarithms, simplify expressions using the rules of exponents, apply the rules of exponents to solve exponential equations in one unknown, simplify logarithmic expressions using the laws of logarithms, identify the relationship between exponents and logarithms, convert between the exponential and the logarithmic forms of equations, apply the laws of logarithms to solve equations, and solve problems involving exponents and logarithms. Now, when we think about exponents and logarithms, we want to know how are exponents and logarithms applicable to everyday life. Well, in everyday life, we use exponents when we're dealing with computers. When we describe a computer's memory, for example, 1 gig or gigabytes of RAM means you have 1 times 10 to the 9 bytes. We use it in finance when we're thinking about calculating interest. We apply it when we're speaking of growth in terms of population growth or bacterial growth, and in medicine to determine how quickly a disease is going to spread. For example, with this COVID-19 crisis, exponents are used in modeling the spread of the COVID-19 virus. In addition, it is used in measurement scales. For example, when we're measuring the strength of earthquakes on the Richter scale. It is used in sound in terms of decibel measurements. And it's also used in chemistry when we think about measuring the pH, which is the acidity or alkalinity of a solution. And finally, in radioactivity, when we're speaking about half-life or decay constants. So we have many applications, and these are just some. It can be applied to many other areas as well. So we will look at exponents and what exactly is an exponent. An exponent is a superscript or a small number written at the top right-hand corner of a number, a variable, or a set of parentheses, and it indicates the amount or the number of times the number is multiplied by itself. So if we look here, we would see we have 2 to the power 3 is equal to 8. So we would refer to this number, which is 3, as the exponent. It is also referred to as an index or a power. And the 2 here, we refer to it as the base, and the result, which is 2 to the power, which gives us 8, the result we refer to as the basic numeral or number. So we will look at some rules of exponents. So the first rule that we have is a to the power n is equal to a times a n times. Essentially, as I stated in the definition, it states the amount of times a number must be multiplied by itself. Therefore, once I have a to the power n, it means whatever n is, I will multiply a by itself n times. So for example, in the previous example that I had with 2 to the power 3, it means I will multiply 2 by itself 3 times. So anything to the power, it means we multiply the number by itself, the number of times indicated by the number. The second rule states that once we're multiplying and the base is the same, once we're taking the product of 2 numbers, what we need to do is to add the power. So once the base is the same and we're multiplying, all we need to do is to take the sum of the powers. The third rule states that once we're dividing and we have a common base, all we need to do is to subtract the powers. Subtract the power in the denominator from the power in the numerator. The fourth rule, it states that once I have anything in a bracket being raised to a power and another power outside, what I need to do is to multiply both powers. So I take the product of both powers. The fifth rule, if I have 2 terms in a bracket being raised to a power, they must be raised individually to the power that is outside. The sixth rule, once I have anything being raised to a negative power I would then write this as 1 divided by a to the positive n, which is the positive power. Continuing, a to the power 1 over n is equal to the nth root of a. Once I have a base being raised to a power that is a fraction, and once the numerator is 1, I simply write it as the nth root of that base. The 8th rule is an extension of the 7th, where instead of having 1 in the numerator, I have a different number. So this I can then separate as two terms. It can be written as a to the m times to the power 1 over n, and applying the 7th rule, I can write 1 over n as the nth root. So it then becomes the nth root of a to the power m. The 9th rule states that once I have a fraction in a bracket being raised to a power, I raise the numerator and the denominator to that power. The 10th rule, an extension of the 9th, once I have a negative power, I simply get rid of the negative by inverting the fraction, and it becomes positive. The 11th rule states that anything to the power 1 is itself. Once I have a base being raised to the power 1, it is always itself. And the final rule states that anything to the power 0 would give me a value of 1. Now, these are a lot of rules, and as you go through, what I would encourage you to do whenever you're practicing, try to write the rules as they are being applied, so that way you will remember them. So we will now go through some examples where we apply these rules. So it says simplify the following. So the first, we're given x to the power 4 times y to the power 3, and we're multiplying that by x to the power negative 7 times y to the power 2, or y squared. So essentially what we would need to do, we have two variables, we have x and y. So what we would need to do, we would have to group the variables and simplify each variable using the rules of exponents. So essentially, we're multiplying. So once we're multiplying, we will apply this rule that states once we're multiplying and the base is the same, all we need to do is to add the powers. So if we're looking for the variable x, the powers are 4 and negative 7. So all I would need to do for the x variable, I simply add these powers. So it becomes 4 plus negative 7, and for the y, it is simply 3 plus 2. Now again, we're looking at the x, so it's 4 plus negative 7. Once the terms are of different signs, all we need to do is to subtract the smaller from the larger and then rewrite the sign of the larger. So in this case, it is 4 plus negative 7. So I can simply write this as 7 minus 4, which would give me 3. And because the larger number 7 is negative, it becomes negative 3. For my y, 3 plus 2 would give me 5. Hence it is x to the negative 3, y to the power 5. But then we have a negative 3 here, and we have a rule which states that once we have anything to the negative power, I simply get rid of the negative by writing it as a fraction. So this x to the negative 3, I now write it as 1 divided by x to the positive 3. I can then go ahead and multiply, and once I'm multiplying, it becomes y to the power 5 divided by x to the power 3. Now we look at the second example here. I have 5x squared in a bracket to the power negative 3. So again, because we have a negative power here, to get rid of the negative power. And to do that, I simply write this as a fraction. So because all the terms are enclosed in a bracket, the fraction would now become 1 divided by 5x squared to the positive 3. I will then apply the rule which states that once I have two terms in a bracket being raised to a power, I raise them individually to the power that is outside. So it means that the constant 5 must also be raised to the power and not just the variable. So it becomes 5 to the power 3, x to the power, x already was raised to the power 2, hence it becomes x squared times 3. We then apply this other rule which states that once I have a term in a bracket being raised to a power, and another power outside, I must multiply both powers. So for my x variable, I'm multiplying these two powers, 2 times 3, hence it becomes x to the power 6. So 5 to the power 3 would give me a value of 125, and x to the power 6. So my final answer would be 1 divided by 125 x to the power 6. We look at another example. It says simplify 16 to the power 3 over 2. Now there are two methods that we will go through. So for the first method, what I'm simply applying the property which states that a to the 1 over n is equal to the nth root of a. So essentially, I have 16 to the power 1/2. I can simply write this as the square root of 16. And usually, you would not see a 2 there, but once you see the square root sign and the number, you're taking the square root. So it is the square root of 16 to the power 3. So we know that the square root of 16 gives us 4, hence it becomes 4 to the power 3, which gives us 64. The second method that we're using is to convert 16 to a base, the lowest base possible. Or in this case, I would convert 16 to a base 4. So I convert 16 as 4 square, and once I have 4 square, I can then go ahead and apply the property which states that once I have 2 powers, I simply multiply both powers. So in multiplying, it becomes 4 to the power 2 times 3 over 2. Now the 2's would cancel, and what I'm left with is 4 to the power 3, which gives me 64. So whichever method you're comfortable with, you can simply apply, you could simply use either method because you will end up with the same value. Another example, I have simplified 3 over 2 to the power negative 3. So again, once I have a negative power, all I need to do is to invert the fraction, replace numerator with denominator, and essentially the power becomes positive. Essentially what you're doing, remember we said applying the property that states a to the negative n is equal to 1 over a to the n. So therefore, if I would simply write this as 1 divided by 3 over 2. And whenever you're dividing by a fraction, all you need to do is to invert and multiply. So then it becomes 1 times 2 over 3, which gives me 2 over 3. And hence, once we have a negative power, we simply invert the fraction and it becomes positive. So I would then apply the rule that states that I raise the power in the terms in the numerator and the denominator individually to the power that is outside. So it becomes 2 to the power 3 divided by 3 to the power 3, which gives us 8 over 27. Right, so now we have a question for you to, I have a question for you to attempt. So it says the expression 8 times x squared to the times y cubed in a bracket all squared divided by 2x y to the power negative 4 simplifies to which of these? So look at the various options A to D and determine what is the solution for this question. So we will go through the solution. Now, for this activity, if you selected A as the correct answer, then you are indeed correct. So we will go through. So we have 8 times x squared y cubed in a bracket all squared divided by 2x y to the negative 4. So the first thing we would do is to expand the powers in the bracket. So we have x squared y cubed in a bracket raised to the 2 that is outside. So we have to multiply the powers in the bracket by the 2 that is outside. So for x, 2 times 2 would give me 4. And for my y variable, 3 times 2 would give me 6. Hence, the numerator becomes 8x to the power 4, y to the power 6. Then I divide 8, so I divide my constants. 8 divided by 2 would give me a value of 4. And then for my variables, I'm dividing, and the base is the same, so I subtract the powers. So it becomes x to the power 4 minus 1, y to the power 6 minus 4. So pay close attention to this. So minus minus, a negative times a negative would give me a positive. Hence, it becomes 4x to the power 3, y to the power 10. Now, if you did not get this correct, what I would encourage you to do is just to go back through the rules, and then make another attempt. So we can solve exponential equations. And an exponential equation is one in which the variable or the unknown occurs in the exponent. The unknown is written as a power. And we will solve exponential equation that can be expressed in terms of a same base. Now, an exponential equation in which each side can be expressed in terms of the same base can be solved using this property. If b to the power x is equal to b to the power y, if we have the same base raised to powers, then x is equal to y. The powers are equal. So once we have a situation where we have the equation with a common base on both sides, we can simply drop the base, apply this property, and equate the powers. So the steps in solving exponential equations of that form: we express both sides of the equation as powers of the same base. Once we have the base, the common base on both sides, we drop the base, we equate the powers, and we solve for the unknown. So we have two examples here. So for the first, I have 3 to the 2n is equal to 81. Now, if we're looking on this side, I have 3n. Now, I can't write 3 as any smaller base, so it therefore means I would need to look at 81 and to see if I can write 81 in terms of a base 3. Now, and essentially to find what that number is, you can, if you don't know it, you can multiply 3 by itself, and you count the number of times that you would need to multiply 3 by itself in order to get 81. So if we multiply 3 times 3 times 3 times 3, we would see that we need to multiply 3 4 times in order for us to get 81. So I can rewrite 81 as 3 to the power 4. Now that I have the common base of 3 on both sides, I can simply drop the base and equate the powers. So equating the powers, it becomes 2n is equal to 4. Therefore, n is equal to 4 divided by 2, which would give me a value of 2. So again, what we try to do, try to write both sides in terms of the common base. Once we have the common base on both sides, we drop the base, equate the powers, and we solve for the unknown. So then we look on the second example here. I have 7 to the power 4n minus 3 is equal to 1. Now, if we're looking at 7, we can't write 7 as a smaller base. If we're looking at 1, you might be saying, but how can I write 1 as anything else? But we're applying this property. Remember, we state that a to the power 0 is equal to 1. So therefore, once I have 1, I can convert it to any base by raising it as the base to the power 0. So because I have a base 7 on that side, I will convert my 1 to a base 7 and write it as 7 to the power 0. So now that I have a common base of 7 on both sides, I drop the base, I equate the powers, and I solve. So it becomes 4n minus 3 is equal to 0. Now the 3 goes across, and once it goes across the equal sign, the sign changes, so it becomes a positive 3. To get n by itself, I simply divide throughout by 4, so it becomes n is equal to 3 divided by 4. So we have a second activity for you to make an attempt at. So here it states if 9x is equal to 1 divided by 27, then x is equal to, so look at the various options and then pick the best solution or the correct answer. Now we will take a break, and while we take a break, you will complete the question and then we will go through afterwards.
You're watching Homeschool 101.
Welcome back. and hopefully you were able to complete the question within the time. So we will go through the solution. So the correct answer for this is actually B. So hopefully that is what you got, and we will go through. So if we're looking at the question, so we have 9 to the power x is equal to 1 divided by 27. Now, a key thing to note is when we're looking at the rules of exponents, you need to know it from both sides. So in this case, I have a fraction here, 1 divided by 27. So I can apply the rule that states a to the power negative n is equal to 1 over a to the n. So I can simply write this as 27 to the negative 1. Get rid of the fraction, and I write it as 27 to the negative 1. In this case, because I cannot write 27 as a base 9, I would then need to write both bases, both 9 and 27, as the lowest base possible. So in this case, I can write 9 as a base 3, and I can also write 27 as a base 3. So 9 is simply 3 to the power 2, and 27 is 3 to the power 3. So once I have this, I would then apply the rule that states that a to the m times n is equal to a to the mn. So I have a power in a bracket being raised to a power outside. So what I would then do is to multiply both powers. So it becomes 3 to the power 2x is equal to 3 to the power negative 3. So now that I have a common base of 3 on both sides, I drop the base and I equate the powers. So it becomes 2x is equal to negative 3. Therefore, x is equal to negative 3 divided by 2, which gives me a value of negative 1.5. So the correct answer is indeed B, negative 1.5. So in this case, if it's not possible to write one base as the other, what you would simply try to do is to get both, write both sides in the lowest base possible. So we've looked at exponents, and we will now proceed to looking at logarithms. Now the definition for logarithm. Now a logarithm, the logarithm of a positive number n to a given base a, is the power to which the base must be raised in order to obtain that number. That is, and the notation, the logarithm of n to the base a is equal to x, and this is what we would refer to as the logarithmic form. And we can also convert from the logarithmic form to the exponential form, which is ax is equal to n. Now we know, as indicated, the exponential form, the unknown or the variable, is written as a power. So for example, the logarithm of 8 to the base 2 is equal to 3. That would be the logarithmic form. And if I'm converting to the exponential form, I simply write it as 2 to the power 3 is equal to 8. So I have an example here. Examples, it states write each exponential form in logarithmic form and each logarithmic form exponentially. So we have 4 questions here, and we will go through them individually. So the first, I have log of 32 to the base 2 is equal to 5. Now, is this in the logarithmic form or the exponential form? Right? Correct. It is in the logarithmic form. And once you see log in the expression or the equation, you know that's the logarithmic form. And to know the exponential form, you would see something being raised as a power. So in this case, the key thing to note, so it's the logarithm of the positive number n to a given base is equal to the number here. So in this case, my base here is 2 in the logarithmic term. So when I'm writing exponentially, that would also be my base. This number 5 here would then become my power. So it becomes 2 to the power 5 is equal to 32. And if you multiply 2 5 times, then you would get the value 32. The second example, I have 4 to the power 3 is equal to 64. So this is in the exponential form. So if I'm converting this to the logarithmic form, then again, my 4 here becomes my base in the logarithmic form. So it's the log of the positive number 64 to the base 4 is equal to a value of 3. Then we look at the third one. Now what you would see is ln, which is the natural logarithms. So the natural logarithms of 20.085536 is equal to 3. Now the key thing, we are looking at logarithm, and the standard base for logarithm is to the base 10. However, we can write in any base. When we're dealing with the natural logarithms, which is ln, our base is e. So therefore, once I see ln, I would simply write in terms of base e. So it would become e to the power 3 is equal to 20.085536. And for the final one, we have e to the power 4. Once I see e, I know I'm referring to the natural logarithms. Therefore, I would use ln. So in the logarithmic form, it would now become ln of 54.59815, and that is equal to a value of 4. Right, so we will look at some laws of logarithms, and we will use these laws when we're simplifying expressions or when we're solving the logarithmic equations. So the first law, it states that the logarithm of 1, regardless of the base, is 0. So it doesn't matter what the base is. Once we're finding the logarithm of 1, it will always give us a value of 0. The second law states that the logarithm of the base itself is equal to 1. Once I'm finding the logarithm of the base, then it gives me a value of 1. So for example, if I have a base 10 and I'm finding the logarithm of 10 to the base 10, that would give me a value of 1. The third rule states that once I have a product, the logarithm of a product is equal to the sum of the individual logs. So once I have a product m times n, it is simply the logarithm of m to the base a plus the logarithm of n to the base a. The fourth rule states that once I have a fraction, the logarithm of a fraction is equal to the logarithm of the numerator minus the logarithm of the denominator. And the final rule states that once I have anything being raised to a power or an exponent, I can simply bring down or get rid of the power by simply multiplying the power by the logarithm. So once I have anything to a power, I can simply take down the power by multiplying the logarithm by the power. So these are the 5 laws that we will look at, and we will now apply them to various questions. So, an example, it states, simplify the following using the laws of logarithms. And a key thing to note is that logarithms and exponents are intertwined. And sometimes, or most times, what you would have to do is to simplify the expression using the rules of exponents, and then you apply the laws of logarithms. So, we have the log of 125 to the base 5. So what we would do is to write 125 as, in this case, because we have 5 here, we want to get 125 as 5 to a power. So I have 125 would be 5 to what power? 125 is essentially 5 to the power 3. So I simply write this as the logarithm to the base 5 of 5 to the power 3. I can then apply this law, which states that once I have a power, I simply multiply the logarithm by the power. So the power here is 3. I would then multiply the logarithm by 3. Hence, it becomes 3 log 5 to the base 5. The law, which also states that once I'm finding the logarithm of the base itself, that is equal to 1. So all of this, log 5 to the base 5, becomes 1. Hence, it is 3 times 1, which gives me a value of 3. We have a second example here. So it is 3 log 4 divided by 5 log 2. So again, although we have a fraction here, and I know many times persons tend to get this, try to think that we're applying the rule that states that the log So looking at this question, and with questions like this, many persons tend to mix this up and try to apply this law. Now, this law cannot be applied here, because if we look at this law gives us the numbers or the terms of fractions m over n. But when we look here, so we have just one logarithmic term and the fraction. But if you look at this, I have a log in the numerator and a log in the denominator. Hence, I cannot apply this law here. This law is not applicable here. So what I would have to do is to try and find another way in order to solve this. So what I can simply do, I can look at the number 4 here and write 4 as 2 to a power. Now I know that 4 is 2 squared. So I would then write this as 3 log 2 to the power 2 divided by 5 log to the log 2. I can then apply this rule, which states that the logarithm of m to the n is equal to n log m to the a. So this then becomes 2 times 3, which gives me 6 log 2 divided by 5 log 2. What I can then do, because the logarithm of 2 is common in both the numerator and the denominator, I can cancel the log 2 from the numerator and the denominator, and that gives me a value of 6 divided by 5. Okay. Another way we can apply the laws of logarithm is to write as a single logarithm. So in my first example here, it says express log 8 plus log 36 minus log 24 as a single logarithm. And essentially we will apply the laws, and wherever we see anything that is being added, we would simply write it as a product. And if anything is being subtracted, I simply write it as a fraction. So if I look at the first two, I have log 8 plus log 36. So I'm applying this law here, which states that once I have a sum, I can write it as a product. So it becomes the logarithm of 8 times 36 minus the logarithm of 24. So 8 times 36 would give me 288 minus the logarithm of 24. Now once I have a minus sign, it simply means I apply this law here and I write it as a fraction. So this becomes the logarithm of 288 divided by 24, and that gives me a value of log 12. For the second example, I have express 1 plus log 15 minus log 25 as a single logarithm. So we have 1 plus log 15 minus the log of 25. Now once I see a number here, I would need to convert this number to a logarithmic expression. So I can apply the law which states that once I'm finding the logarithm of the base itself, it is equal to a value of 1. And in this case, remember I said the standard base for logarithm would be a base 10. And once we don't see a number there, it is understood to be logarithm to the base 10. So therefore, if I'm converting 1 to a base, to the base, then I would simply write it as a logarithm of 10, knowing that it's the logarithm of 10 to the base 10, logarithm of a to the base a, which gives me a value of 1. So now that I have them all in terms of logarithm, I can go ahead and apply the various laws. So again, once I see a plus sign, I write it as a product. So it becomes a logarithm of 10 times 15 minus the logarithm of 25. So 10 times 15 would give me 150. Again, once I have the minus sign, I simply write it as a fraction. So it becomes the logarithm of 150 divided by 25, which gives me the logarithm of 6. So we have a third activity, so you can apply what we just went through. So it says the logarithm of 16 minus the logarithm of 2 is the same as. So look at this question to see which laws can be applied and which of these would be the correct answer. All right, so we will go through. So what I will do, I will go through from here and then I'll turn to the correct slide, with the slide with the answer. So if we are looking at the first option, now again, as indicated, I know some persons, if you selected A as the correct answer, that is incorrect. Now, as I said, and persons tend to think that is the same thing as m over n is equal to the log of m minus the log of n. So if you stated the first one, that is incorrect. The correct rule is the logarithm of m over n is equal to m minus n. So in this case, the correct one is actually B, which is the logarithm of 16 divided by 2. Once we have a negative sign, we write it as a fraction, and when we're writing it as a fraction, it should be just the logarithm of the fraction, not the log of the number divided by the log of the other as indicated in A. All right? So our correct answer, the log of 16 over 2. We can use logarithms to solve exponential equations. So I have a to the power x is equal to b, that's an exponential equation, and we will use logarithms in order to solve these exponential equations. So the steps would be, you take the logarithm of both sides of the equation, you then simplify using the properties or the laws of logarithms, and then you solve for the unknown. So an example here, I have solve 4 to the power x is equal to 100, and again we know it's an exponential equation because the unknown is written as a power. So in applying logarithms, as indicated the steps, the first thing we do is to take the logarithm of both sides. So as I indicated, we can use LOG, which is the logarithm to the base 10, or we can use the natural logarithms, which is ln. So I will go through using logarithm to the base 10. And the key thing to note, on your calculators, you can only find logarithm to the base 10 or the natural logarithms. So we can only find the logarithm to the base 10 on our calculators. So it's the logarithm. So we take the logarithm of both sides. We would then apply the property which states that once we have a power, we simply multiply the logarithm by the power. So here the power is 4. I would then multiply the logarithm by that power. So it becomes x log 4 is equal to log of 100. Make x the subject by dividing by log 4, so it becomes log 100 divided by log 4. And you would find these individually in your calculator, and then you write the value. And a key thing to note when entering this in your calculator, it is always best to enter log 100, find what that value is, and then the other. So find them individually, write them as a fraction, and then you write the correct answer. So in this case, x is equal to 3.322. As I indicated, you can also use the natural logarithms, and even though the individual values would differ, the final answer is the same. So it becomes ln 4 to the power x is equal to ln 100. We apply the same property, we multiply by the power, so it becomes x ln 4 is equal to ln 100. So x is equal to ln, or the natural logarithms of 100 divided by the natural logarithm of 4. Find these individually, then place in the fraction, we end up with a value of 3.322. So whether we use LOG or we use ln, we end up with the same final result. Now we will look at solving equations where we actually have logarithms, or the logarithmic equations. So the steps, and step 1 to 2, this is only in the case where you have more than one logarithmic term. If you have only one logarithmic term, then you can go straight to step 3. So once we have one or more than one logarithmic term, we need to group them all on one side, on the left-hand side. We would then need to convert them to a single logarithm using the laws of logarithm. The third step would be to convert to the exponential form, and then we solve for the unknown. So I have an example here. So in this case, I have only one logarithmic term, therefore I would bypass the first two steps. So I would move straight to the third step, which is to convert to the exponential form. So how do I convert to the exponential form? So the first thing we would need to know, what is the base here? And in this case, remember I indicated once a value is not seen, the base is 10. So we're operating as if a 10 was here as the base. You don't see it, but it is base 10. So to convert to the exponential form, it's simply the base raised to the power is equal to the 2x. So it becomes 10 to the power 3 is equal to 2x. 10 to the power 3 is the same thing as 1,000, so 1,000 is equal to 2x. Therefore, to find x, I divide 1,000 by 2, and that gives me a value of 500. So in this case, when we solve, we simply end up with a value of 500. And a key thing to note, whenever you're given logarithmic questions, it is always good to test that they're actual solutions. So once you get the value of x, you simply just substitute back in the equation just to double check that it is actually a solution. I have a second example here. So it says solve the logarithm of x to the base 6 is equal to 2 minus the logarithm of 4 to the base 6. So in this case, I have two logarithmic terms. So therefore, I have to start from step 1, and the step 1 states that I take them all to the left-hand side. So therefore means this negative log of 4 to the base 6, I need to take it on the left-hand side. Note the sign, this is negative, and once it goes across the equal sign, it becomes positive. So this is now the logarithm of x to the base 6 plus the logarithm of 4 to the base 6 is equal to 2. Now the key thing, note that this number, we would not convert this to a logarithmic term. It would, once it's an equation, it would remain as is, and we leave it as such. We don't need to convert it to a logarithmic term. What we will then need to do is to convert this to a single logarithm using the laws of logarithm. Now in this case, I have a plus sign, and the law that we will apply is the one that states once we have a plus sign, we write it as a product. So this would become the logarithm of 4 times x to the base 6. So once it's a plus sign, we then multiply both terms, so 4 times x would give us 4x. Now that we have it in the form of a single logarithm, we would then need to convert to the exponential form. So in this case, my base here is 6. So in converting to the exponential form, it becomes 6 squared is equal to 4x. I'll just switch it around so that I have my unknown on this side. So I have 4x is equal to 36, which is 6 squared. So therefore, x would be equal to 36 divided by 4, which gives me a value of 9. So again, once we have a logarithmic equation, if there are more than one logarithmic term, group them all on the left-hand side. You then simplify or write as a single logarithm using the laws of logarithms. Once you have it as a single logarithm, you then convert to the exponential form and then solve for the unknown. All right. Now I have a final activity for you to attempt. So it says if the logarithm of the cube root of y is equal to 1/3, then y is equal to. Go ahead and make an attempt at this question. And we will take a break while you go through the question to give you time to go through, and then we will return.
You're watching Homeschool 101.
So welcome back. So what did you find as the solution for this activity? Which of the options was it? A, B, C, or D? Now if you said D, you are indeed correct. If you had any other option, it is incorrect, and we will go through. Right. So if we are looking at the solution, so we're given the logarithm of the cube root of y, and we are told that this is equal to 1/3. So what I would simply do, the first thing I would do, so this cube root of y, remember again I said you need to apply a lot of exponents. So we're applying the property which states that the nth root of a is equal to a to the 1 over n. So because I have that as the cube root of y, I would simply write this as y to the power 1/3. So it becomes what logarithm of y to the power 1/3 is equal to 1/3. So because this is a logarithmic equation, what I would need to do is to convert to the exponential form. So in converting to the exponential form, remember again the base here is 10 because the value is not given. So it's 10 to the power, or it's 10 because it's the standard base, and once I don't see a value, then I know it is 10. So it is 10 to the power 1/3 is equal to y to the power 1/3. So therefore, what I would need to do is to cube both sides, and that would give me y to the power 1. So if I cube both sides, I would then apply indices again by multiplying both powers. So 1/3 times 3 would give me 1. So it becomes y is equal to 10. So in this case, my correct answer is indeed 10. So that brings us to the end of today's class, but just to recap, we looked at real life applications of exponents and logarithms. We would have covered the rules of exponents. We simplified exponential equations. We solved exponential equations in one unknown. We looked at the laws of logarithms, the relationship between exponents and logarithms. We looked at converting between exponential and the logarithmic forms of equations. We simplified logarithmic expressions, and we also solved logarithmic equations. Now, what I would encourage you to do as we went through this topic, just go back through the questions, practice, 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 because the key is practice. So all the best, and see you at the next class.
You've been watching Homeschool 101, a partnership between ABS Television and the Ministry of Education. Thank you for viewing this lesson. Join us again next time.